Again, this is very important exercise. We need to evaluate the surface integral where S denotes the surface of the cube bounded by the planes x equal to 0, x equal to a, and then y equal to 0, y equal to a, and then z equal to 0, z equal to a by using the Gauss's divergence theorem. And also we need to verify the result by direct manipulation. To solve this integral, let's use Gauss's divergence theorem first. So let V be the region enclosed by the surface S, and let's take F vector to be this one. And then by Gauss's divergence theorem we have the result. The surface integral of the dot product of F vector with dA vector. Why I have taken the dA vector? Because here it is given to us that you should use the dot product with dA vector. This dA vector is also equal to n vector ds, which I have used in the previous exercise, right? In the previous exercise, I have used the Gauss's divergence theorem using this n vector ds instead of dA vector. So either you can use dA vector or you can use n vector ds, dot product with this f, right? So the surface integral of dot product of f vector with dA vector is equal to the volume integral of the divergence of f vector dv, which can also be taken as the surface integral of f vector dot, because dA vector is n vector ds. So this is also equal to the volume integral of divergence of f vector dv. So I'm going to use this result. So the surface integral of f vector dot n vector ds equals to the volume integral of divergence of f vector dv. So we need to calculate the divergence of f vector first. This is your f vector. Okay. What is the divergence of f vector? So it is curly over curly xi cap plus curly over curly yj cap plus curly over curly zk cap. It's dot product with this f vector. So this is xi plus yj plus zk. So when taking the dot product, what we get? Curly by curly x of this x. So curly by curly x of x plus curly by curly y of y plus curly by curly z of z. Derivating x with respect to x is 1. Derivating y with respect to y is also 1. Derivating z with respect to z is also 1. So this is equal to 3. So it is the volume integral of divergence of f vector is 3, and this is dv. Writing the triple integral 3, and this is dx, dy, dz. Limits are given to us. The limits for x is from 0 to a, for y is also the same, for z is also the same. So this is 0 to a, 0 to a, 0 to a. Separating them. Integrating 1 with respect to x gives x, and then limits from 0 to a. Integrating y with respect to 1 gives y, and then z. So when putting the upper limit, we get a minus the lower limit, a minus 0, and then again for this also a minus 0, and then a minus 0. So that gives 3a cube. So this is a required answer for the surface integral, and please mark this as 1. And now we are going to evaluate the surface integral directly and then check the result whether it is coming out to be 3a cube or not, right? So for this, I have taken these three x's, x, y, z, and this is the surface, that is the cube. And this cube is consisting of 6 faces, right? So the surface S consists of 6 faces, and we are going to evaluate the integral over each of these 6 faces. So let's first evaluate the integral over the surface O, B, and A, this one. And here the outward unit vector normal to the surface is, because it is along the negative z-axis, so I am taking this to be minus k. And for this, ds is equal to, yes, dx dy. So the surface integral of f vector dot product with dA vector, I am taking this to be as another way. So it is n vector ds. dA vector is n vector ds. So this is equal to the surface integral of This f vector, yes, and n vector is minus k, and ds is dx dy, right? This is your double integral. When taking the dot product, we get minus z dx dy, and the limits from 0 to a, 0 to a. Okay, on this surface O, B and A, yes, z is 0, so this is equal to the double integral. This is minus 0 dx dy, as z equal to 0 on O, B and A. This integral comes out to be 0. Please mark this as 1, and let me mark this as star. And then let's evaluate the integral over this surface. That is the opposite for this. And here the unit vector is along the z-axis. Yes. So this is equal to k vector. And ds is equal to the same dx dy. This is along x-axis and this is along y-axis, right? So dx dy. So here n vector is k vector, and this is equal to the double integral. When taking the dot product, we get z dx dy, and the limits from 0 to a. Now here z is equal to a, right? This is also a, this distance is also a, and this distance is also a. So here on this surface z is equal to a. So writing here a dx dy as z is equal to a on PLCM, right? Taking this a outside, and when you solve this integral, you get a into a, which is equal to a cube. And now let's evaluate the integral along this surface OBLC. And here the outward unit vector drawn is along the negative x-axis. So this is minus I cap, and ds is equal to dy dz. Please remember, whatever may be the direction of the unit vector outward drawn normal to the surface, take the ds to be equal to the product of other two x's. If the unit vector drawn is towards the x-axis, whether negative or positive, you have to take your ds to be dy dz. If unit vector drawn normal is along the y-axis, then take your ds to be dx dz, skipping this y, right? If the unit vector drawn is along the z-axis, take your ds to be dx dy, no matter in which direction unit vector is taken. Negative z-axis or positive z-axis, you have to take your ds to be dx dy, right? So for this surface, n vector is minus I vector, yes. So this is equal to the double integral. When taking the dot product, we get minus x, and this is dy dz. Limits from 0 to a. Now on this surface, x is 0. X is 0 on OBLC, right? So this is equal to the double integral from 0 to a. This is 0 dy dz. So this integral is 0. Please mark this as 3. Marking this as 2. Now calculating the surface integral over NPMA, that is the opposite of this. That is this one. Now here outward unit vector drawn is along the positive x-axis. So taking n vector to be I vector, and ds is, yes, it is again dy dz, same. So here n vector is I vector, and this is double integral. When taking the dot product, we get x, and this is dy dz from 0 to a limits. What is the value of x here? Here x is having the constant value a, right, from 0 to a. So on this surface, x is equal to a. So this is double integral, and this is a dy dz. Taking this a outside and integrating 1 with respect to first dy. So this is a from 0 to a. This is y from 0 to a dz. So putting the upper limit, we get a minus the lower limit, that is 0. So this is your a. So taking this a outside, it becomes square. And now integrating 1 with respect to z, that gives a square into a, that is equal to a cube. And now over the surface OCMA, that is this one. And here the outward unit vector drawn is along the negative y-axis. So take n vector to be minus j cap. And because it is along the y-axis, so we are taking ds to be dx dz, skipping y, right? And on this surface, y is 0. So n vector is minus j cap. So this is double integral. When taking the dot product, we get minus y dx dz. And on the surface, y is 0. So y is 0. So this integral is coming out to be 0. Please mark this as 5. And then over the surface BLPN, that is opposite to the blue surface. And here the outward unit vector normal to the surface is along the y-axis, that is equal to j. And taking ds to be, because it is along the y-axis, so ds is same as this dx dz. And here on the surface, y is having the constant value a, right? So n vector is j vector, and when taking the dot product, we get y dx dz, limits from 0 to a, and on this surface, y is equal to a. So y is a dx dz, taking a outside, and then integrating 1 with respect to x, we get a. Same integration 1 with respect to z, we get again a. So this is a cube. Please mark this as 6. And now we are going to add all these 6 integrals, and what we get, the value for the first integral is, so when you add all these, you get 3a cube, which is same as this, the result we got from the Gauss's divergence theorem, right? So which is same as star, hence the verification. Alright, thank you, stay blessed.